Welcome to the solutions for the Advanced Placement Kinematics problem set numbers 13, 14, and 15. Let's go ahead and get started with 13. We have the engine of a model rocket accelerates the rocket vertically upward for 2 seconds as follows. At t equals 0, the rocket speed is 0. At t equals 1 second, its speed is 5 meters per second. And at t equals 2 seconds, its speed is 16 meters per second. They want us to plot a velocity versus time graph for this motion and then use the graph to answer a couple questions. Pause the video at this time to construct your graph just with the axes appropriate to scale and the data points plotted, and then resume the video when that's complete. All right, here we are back at the questions that we need to answer here. We have A, they want the rocket's average acceleration during the 2-second time interval. Well, the key here for the acceleration, if they want the rocket's average acceleration, so we'll underline that is the slope of the fit line to that data. So now, as we come back and we take a look at your graph, what you need is a slope to the best fit. You need a best fit line to the data that you plotted here. And then you have to go ahead and calculate that slope, and you should find an answer that's close to the slope done on the computer here, which was 8.00 meters per second, or meters per second squared. We'll show you that derivation here at some point during class. The second one asks us for the instantaneous acceleration of the rocket at time equals 1.5 seconds. And to do the instantaneous acceleration, just like in the previous graph, we would do the slope of a tangent. So one thing we want to point out here is that whenever you're asked for the average quantity from a graph, you're typically going to do the slope of a best fit straight line. And when you're asked for an instantaneous quantity, you're going to do the slope of a tangent. So we'll start over here with the graph redone with a best fit curve, which really does show on a velocity time graph that the acceleration is changing. And they want the slope of the tangent line at 1.5 seconds. So the first thing we're going to do is to draw a tangent line at 1.5 seconds. We'll go and adjust that so that it's just touching the curve at that spot. May need to adjust a little bit here and there to do it. Trying to get it to move here. There we go. And then the next thing we want to do is we want to really extend that tangent line as far up and down as we can. Okay, I'm going to make this a different color to make it stand out. Okay, and now what we need to do is we need to find the slope of that tangent. So what we have to do that is to select 2 points that intersect a grid pattern on our graph. Looks like there would be one there, and looks like another one down here. We want to use those 2 spots to calculate a change in y over our change in x. Okay, so we're going to go ahead and do that, and then the slope is our instantaneous acceleration. What's our y information here? Our final y value looks like it's 14. Our initial y value looks like it's 3. Our final x value looks like it's 1.9. And our initial x value selected looks like it's 0.9. 14 minus 3 is 11. And 1.9 minus 0.9 is 1. And so our instantaneous acceleration is 11 meters per second squared. So that's how you would do that. Okay? All right, let's move on to number 14. We have a speedboat increases its speed uniformly from 20 meters per second. What does that indicate to us? It indicates to us that that's the speedboat's initial velocity, to 30 meters per second, indicating to us that's the speedboat's final velocity, in a distance of 200 meters. And that's the x value provided. Find the magnitude of the acceleration, a, and the time it takes the boat to travel the 200 meters, and that would be t. So looking at that, we have VO, V, and X as given quantities, and that we want to solve in A for the acceleration. We go to the reference table to see if there is an equation that we could use to accomplish this calculation in one step. So we're looking for an equation that has VO, V, X, and A in it. And we believe as we inspect, we find that there is, and it's V squared equals VO squared plus 2AX. So go ahead and we substitute in. Our final velocity is 30. Remembering to square that. Our initial velocity is 20. Remembering to square that. Plus 2A, and our distance is 200. Solve this algebraically for A in as many steps as you need to do that. Pause this video before doing that to check your answer. And when you're done, you should get an answer that's 1.25 meters per second squared. Okay? For B, they want the time it takes the boat to travel the 200 meters. And so we have initial velocity, final velocity, x. We now also have A, our acceleration. So it makes sense that we would use the most simplest form here. Now I'm going to show you where that comes from. And I'm going to do this in red. Red meaning danger. Because there's a lot of people that say, oh, I'll just use A equals delta V over T. And that's great, provided that you use the literal meaning of change in velocity, which is final minus initial. A change in any quantity is always its final value minus its initial value. The danger in using this, of course, is that you just simply take the big number minus the small number, divide by the time, and say that that's your acceleration. The problem is that if the object is slowing down, that the final value is going to be less than the initial value, and you should get a negative acceleration on that. And if you go forward and use that value in any future calculations, you're going to get wrong answers. So that's why it's a dangerous thing to do. But I'm going to show you here, if we take and multiply this equation that we've derived so far, if we multiply both sides by t, we get an AT over here equals V minus VO. And then if we take and add the VO to the other side, we get VO plus AT equals V. And essentially what you have rearranged is that value, that equation, sorry, is the one that's provided in the reference table. I would encourage you to use this version of that equation because it takes away from you having to remember this is just a direct substitution equation. So we'll start with V equals VO plus AT. Now having shown you the derivation of that, final velocity is 30, initial velocity is 20, plus A 1.25, and our time is what we're looking for. We go ahead and algebraically solve for t. Once again, pause the video if you need time to do that. Do that in as many steps as needed for you. And we should get an answer that is 8.00 seconds. Okay? All right, we finish up with number 15. Let's label the information we've given here. A driver in a car traveling at a speed of 60 miles per hour. So that's key information. We're not sure what the rest is here, so we'll just start with a V. Sees a deer 100 meters away. That's distance or displacement on the road. Calculate the minimum constant acceleration, A, that is necessary for the car to stop. If it's going to stop, that means its final velocity, that makes the initial velocity up here as the 60 miles per hour without hitting the deer, assuming the deer is not moving in the meantime. This picture of this deer is the definition of the doe or the deer in the headlights look. So we'll see if we can save the deer here. We have initial velocity, we have x. We're looking for a final velocity, and we have a. So again, we go to the reference table looking for an equation that relates the variables we have to work with. If stop means the final velocity is going to be 0. And once again, we land on v squared equals VO squared plus 2AX. So V is 0, so 0 squared is 0, VO, danger here in substituting the 60. You might remember that earlier we had a follow-up question that asked for the conversion between 60 miles per hour and how many meters per second that is. We'll flip back and use that derivation. And I remember that it's 26.8 meters per second to 3 digits, just 27 meters per second to 2 digits. So we'll use a 3 sig fig value there, 26.8 squared plus 2a, and our stopping distance has to be 100 meters. Solve algebraically for a, pause if you need time to calculate, and we get an answer that is 200. I apologize, the wrong thing here, negative 3.59 meters per second squared. Alrighty, so some introductory calculations here with some kinematics problems, and obviously we'll have much more practice with this in class.